everyone. As I still see a lot of other attendees are trying to join the webinar, maybe we can wait for another 2 minutes and then we will get started. All right, I'm going to get started. Welcome everyone. This is Boston chapter of the ASA's first webinar in year 2023. I am Wenting Chen, the president of the Boston chapter and a statistician and Bayesian. We are very pleased that you are joining us today, and we have the great pleasure that Professor Ying Yuan from MD Anderson Cancer Center will give a review of the BoIN designs today. This webinar is moderated by Dr. Zhaoyang Ten, Biostatistics Director, Head of LCM Biostatistics for Oncology, Head of Biostatistics in APAC at Savir Pharmaceuticals. Now I will hand it over to moderator Zhaoyang so that he can cover the logistics and introduce today's speaker.
Okay, thank you, Wenting, and hello, everyone. This is Zhaoyang Teng from Savir Pharmaceutical. So I will serve as your moderator for today's webinar. As Wenting just introduced, our speaker today is Professor Ying Yuan, who is a Batian Ash Marie Distinguished Professor and a Deputy Chair in the Department of Biostats at the University of Texas MD Anderson Cancer Center. Professor Yuan has published over 100 statistical methodology papers on innovative Bayesian adaptive designs, including early phase trials, seamless trials, biomarker-guided trials, and basket and platform trials. The design and the software developed by Dr. Yuan's lab has been widely used in medical research institute and pharmaceutical company. The BoIN design developed by Dr. Yuan's lab, which is also the topic of today's webinar, is the first oncology dose-finding design designated as fit-for-purpose drug development tool by FDA. Dr. Yuan was elected as ASA Fellow and wrote the book Bayesian Design for Phase 1-2 Clinical Trials and Model Assistant Bayesian Design for Dose-Finding and Optimization, published by Chapman and Hall CRC. So before I give the stage to Professor Yuan, I would like to remind everyone some logistics of today's webinar. So Professor Yuan will give a presentation of about 45 minutes, followed by a 15-minute Q&A session. However, if you have any clarification question related to his presentation that you want to ask during his presentation, you can still ask that, but please type your question in the Q&A. I will read your question to Professor Yuan to answer. For any other logistic questions, so for example, if you cannot hear us or you have any question related, whether the webinar will be recorded or where to get those slides, you can type that in the chat box. So lastly, the webinar will be recorded and available afterward along with the slides. Without further ado, I think Professor Yuan, the stage is yours.
All right. Good evening, everyone. First, I'd like to thank Zhao Yang for the nice introduction and Boston chapter for the invitation. So today, this outline, and I will very briefly overview phase 1 trial designs, and then move to the main topic, based on optimal interval design. And I will talk a little bit about methodology and a case study, and followed by a BoIN suite, which is a software platform can be used to implement BoIN methodology. So the objective of phase 1 trial is to find the MTD, maximum tolerated dose. And statistically, it's defined as a dose which has a toxicity equal or close to a target toxicity rate. Here we denote the phi. For example, a lot of time we are looking for 25 or 30%. So many designs have been proposed for phase 1 trial, and they can be classified into 3 groups: algorithm-based, model-based, and model-assisted. For algorithm-based design, a typical example is 3+3, and we're all very familiar. And 3+3 design, it's transparent, easy to implement, but it has a poor performance. So to address that issue, a statistician developed a model-based design. And the basic idea is pretty straightforward. We propose a parametric model, describe those toxicity relationship. And then based on the observed data, we keep continuous updating the estimate of those toxicity curve. And based on the estimate, we make a decision of dose escalation and de-escalation. A typical example is the CRM and its extensions, for example, EVOC and BRM. And this class of design has a superior performance, but it's less transparent and difficult to implement. So here is a quick example regarding the model-based design. And this is the CRM based on a Bayesian logistical model. And you can see there's 2 parameters, alpha and beta, and the slope and the intercept. And we also assign prior to those 2 parameters. And once we have data, we update our estimate to make a decision, dose escalation and de-escalation. And you can see this is relatively complicated. And first, we have to specify prior for the alpha and the beta, which actually is more involved than we thought, typically thought, because it's a small sample size. It's pretty, we need a very careful to specify the prior, which has quite a bit of impact on the operating characteristic of the design. And also, once we get data, we have always fit the model, make a decision. So a model-assisted design has been proposed to combine the advantage of algorithm-based design and model-based design. So basically, it's a class of designs that utilize the model for efficient decision-making. And this is very similar to model-based design. But it's dose escalation, de-escalation rule can be pre-tabulated and before onset of the trial, including in the protocol. So when we do the trial, it's kind of like algorithm-based design. And the example of model-based assist design, including the MTBI, BoIN, and the keyboard design. And today we will mainly focus on a BoIN family design. Okay, so this is always the cartoon I want to, as analogous to show the model assist design. At the back end, we work hard to figure out all the model's decision rule. And for user, and you just need to sit down, relax, and enjoy the design. Okay, so this is a BoIN design. It's pretty straightforward. And what we do is we compute the DLT rate at the current dose. And if that rate is less or equal than lambda E, which is we call the escalation boundary. That's you see the subscript E means escalation. We escalate the dose. And if the DLT rate is greater than lambda D, the de-escalation boundary, we de-escalate. And if the DLT rate is between escalation and de-escalation boundary, we stay at the current dose to the next cohort patient. And the computation of the DLT rate is trivial, which is defined at the bottom, which is the number of patients treated at the current dose with DLT divided by the number of patients treated at the current dose. If we treat 3 patients, 1 DLT, that's 33%. If we treat 4 patients, 1 DLT, that's 25%. It's very easy. And that's also the very intuitive way for non-statistician to understand the DLT and the toxicity rate at the current dose. And in the BoIN design, the only two design parameters is escalation and the de-escalation boundary. So in the table in the bottom, it shows the escalation and de-escalation boundary for the common used target toxicity rate. So for example, we want to design phase 1 trial with the target toxicity 25%. And then the escalation boundary is 0.197 and the de-escalation boundary is 0.298. If we plug in, this is the design. It's very simple, right? Every time you just compute the DLT rate at the current dose. If that DLT rate is less or equal than 0.197, we escalate. If it's greater than 0.298, we de-escalate. If it's between, we're going to stay at the current dose and treat additional cohort patient. So in some sense, it's very hard to imagine any other design can be simpler than this, right? Even 3+3 design, you have to remember different rule for 3 patient and 6 patient, which actually are slightly different. But in here, the only thing you have to remember, you have to use is those two boundaries, escalation boundary and de-escalation boundary, and that's it. Okay, before we go to the theory, how that design has been derived and what's the statistical principle behind it, we first take a look how we conduct the trial in practice. What we're going to do is we're going to start the trial by treating the first cohort of patients at the lowest or pre-specified starting dose level, which typically is the lowest dose, right? And we treat the first cohort patient at the lowest dose. Then when the second cohort patient comes, we have 3 possible decisions for the second cohort patient. We can escalate the dose, de-escalate, or retain the current dose. So let's assume if we knew the true toxicity rate of the current dose, and here we use J denote the current dose level, and the PJ denote the true toxicity rate for the dose. And then decision going to be pretty simple, right? Because we have our target fee, that's what we want, 25% or 30%. And if the PJ less than phi, that means the current dose is below the MTD. The decision definitely is escalate dose, right? And then when the PJ is greater than phi, that means the current dose already above the MTD. The decision going to be de-escalate. And if PJ equals to phi, we're going to stay at the current dose because that's the MTD. Once we treat that second cohort and the third cohort patient arrive, and we face the same decision, right? We can either escalate dose, de-escalate dose, or stay at the same dose. Again, if we assume we always knew the true toxicity rate at the current dose, then the decision is simple, exactly same as before. If PJ less than phi, we're going to escalate. If PJ is greater than phi, we de-escalate. If PJ equals phi, we're going to stay at the same dose to treat the next cohort. And we just repeated the above step of dose assignment until the trial is complete. For example, we have a maximum sample size. We reach that maximum sample size. We stop the trial. We complete the phase 1 trial. So what that means? So this means the phase 1 trial can be viewed as a sequence of adaptive decision-making steps of dose assignment for patients who are sequentially enrolled into the trial. And if the PJ was new, we obtain the so-called oracle design. So why is oracle? Because it's a perfect design. There is no decision error, right? Every time we make a correct decision, because we know the true toxicity rate of the current dose. If it's lower than MTD, we're going to escalate. If higher than MTD, we're going to de-escalate. If it is the MTD, we're going to stay at that dose. That means there is no error. And also from patient perspective, it's also optimum dosing for each patient. But the reason it's called an oracle is because it does not exist in practice. And we never know the truth, right? If we knew the truth, there's no reason we do the phase 1 trial. And what we can do is make a decision based on the observed data. And how can we make optimal decision based on observed data? And natural thinking is we trying to minimize the chance of incorrect decision and get the design as close as possible to the oracle design. Oracle design is a perfect design. And we're trying to get as close as possible to that perfect design based on the observed data. And if we go through that exercise, and the optimal solution is the BoIN design. So once you get the rough idea how it works, and then we can go to detail, how the design is derived and how the decision error is minimized. So in order to do that, I introduce a few notations. So here we use capital J denote the total number of dose under investigation, 5 dose, 4 dose. And the phi is our target DLT rate, 25%, 30%. And the PJ is the true DLT rate at the current dose, okay, dose level J. And the PJ hat is the observed DLT rate at the dose level J. Now we first introduce a class of non-parametric design, okay? And the basic idea is we're gonna optimize the performance within this class of non-parametric design. So in other words, we're trying to find the optimal design within this class. Okay, how this non-parametric design looks like. So the first is we're going to treat the first cohort patient at the lowest or pre-specified dose. And then at the current dose level J, if the PJ hat, the observed DLT rate, less or equal than lambda 1J NJ, we're going to escalate the dose. And if it's greater than lambda 2J, we're going to de-escalate. And otherwise, we're going to stay at the same dose. And we repeat step 2 until the maximum sample size is reached. So one thing I want to highlight here is the boundary is slightly different from I first introduced the BoIN design, right? We have lambda E, lambda D, 2 fixed number. Notice here, the lambda 1J, lambda 2J is a function. It's an arbitrary function of dose level J and the number of patients treated. And then you can imagine at any time, any dose, this boundary can be changed freely. So which means all the design, non-parametric design, without assume parametric assumption on the dose toxicity curve are all included in this family. So this is a huge family, okay, including all the possible decisions, because at any time you can change your boundary. And then you can remember, you can notice that because the number of patients is a discrete, right? So if anytime you can change the boundary, basically you enumerate all the possibility, all the possible decisions you can make. Okay. Once we have that big family of non-parametric design, our goal is trying to find the optimal design within that family. So in other words, back to here, we're trying to find the optimal boundary, lambda 1J, lambda 2J, to minimize decision error. And then in order to do that, we first have to define what's the decision error, right? And then we can minimize it. And then in order to do that, we introduce 3 hypotheses, okay? The first hypothesis is a target dose, okay? So for this one, it's obvious it's pre-specified by the trial. So what the user have to specify is the 2 alternatives. One we call a low alternative, which means under this toxicity rate, escalation is needed. So that means this dose is really underdosing, subtherapeutic. We must escalate, okay? So on the other side, we also introduce high alternative, we denoted by phi2, which means under this toxicity rate, the escalation is necessary. That means this dose is really, really toxic. We have to de-escalate, okay? So once we have this, we can just assign 3 hypotheses, denote those by 3 hypotheses, right? So we use H0 denote that's the MTD, PJ equals phi, and H1 denotes the PJ equals phi1. That means the underdosing, we really need to escalate. And H2 denotes the case, it's really overdosing, we need to de-escalate. So once we have those hypotheses, 3 hypotheses, and then we can write down the decision error as shown in these slides. So basically it consists of 3 terms. Okay, so we first look at the first term. Actually pretty straightforward. So this first term have 2 parts. The first part is the probability of H0. So which means the likelihood that dose is the MTD. Okay, and the second term means given that dose is the MTD, how likely you escalate or de-escalate. And we know under the H0, which means it's the MTD, the correct decision is should stay at that dose. If we escalate or de-escalate, it's incorrect decision. So the first term describe one type of error, decision error. And because we have three status, right? MTD, underdosing, overdosing. So the other two terms capture the other two cases. And the second term means what's the probability H1 is true? That means the underdosing. And given it's underdosing, how likely, what's the probability make a decision of de-escalate and stay? Because in this case, the correct decision should be escalate because we are underdosing. And the second term, it's also the second type of decision error we may have. And that's the last term, it's for the overdosing. And then we can plug in those probability and use the decision rule we have. And because the number of toxicity is a binomial distribution, when you go through those, essentially, it's going to be a binomial density, a function of binomial density. So one thing I want to highlight here, you will notice this error, decision error, is a function of lambda 1j, lambda 2j, right? That's the key point you want to take from the slides, okay? And then the next step is we trying to find the lambda 1j, lambda 2j to minimize that decision error. And what you can do is you can take a derivative of lambda 1, lambda 2j and set 0 and solve the lambda 1j, lambda 2j. And if you go through that exercise, amazingly, the solution first has a closed form. Okay, it's showed here, lambda e, lambda d. And the really striking is those two boundaries are independent of nj and j. So notice when we introduce the class of design, we allow lambda 1j, lambda 2j is an arbitrary function of sample size, number of patients treated at the current moment, and also the dose, those one or those two, and so on. But eventually, the optimal solution is independent of nj and j. And this makes BoIN extremely simple, as we showed at the beginning. You just compare with those two fixed boundaries. So that's why we get just a nice, very clean form. If you target 25%, you just compare with 0.197 and 0.298. Okay, it's very simple, right? But how about performance? And in this review paper, and the authors compared many commonly used innovative design, including the CRM, BORM, and MTPI, BoIN, and so on. And the conclusion is the BoIN yield competitive performance comparable to the CRM, but it's simple to implement, and also free of the issue of irrational dose assignment caused by model misspecification. And if you are interested, you can look at this paper. There's a lot of simulation results over there. And so I always like this quote: simplicity is ultimate sophistication. And because it's very simple, transparent, and also have a good, robust performance, and so it has received fit for purpose designation from FDA. Okay, so I'm gonna next. So I'm gonna I'm trying to answer some frequently asked questions to help you further understand design. Okay, the first question is: the BoIN does not borrow information across those, and is it less efficient for model-based design such as the CRM or BORM? Right. Remember, in the BoIN, what you do is you just calculate DLT rate at the current dose compared with those two boundaries. You don't use the data directly from other doses, only the current dose. So the answer actually, it's a little bit anti-intuitive, not really. Okay, why is that? So in the bottom, I'm going to show you some intuition why that's the case. So let's imagine, okay, right now we are at dose level 3, which shows that's green. And remember, in order to reach dose level 3, we must treat the patient at dose level 1 and 2, and also the data must show those two doses pretty safe, right? Otherwise, there's no chance we're going to escalate to dose level 3. Now, that's the key point, okay? So the dose level 1, 2, the data shows it's pretty safe. That's why we escalate dose level 3, which means the data at dose 1 and 2 does not really provide much information regarding if the dose level 3 is below the MTD, is MTD, or above MTD. In a simple case, you can imagine we have 0 toxicity or 0 out of 3 toxicity in 1 and 2. Based on that information, it cannot tell you much about the toxicity of dose level 3, right? It can continue 0 out of 3, or 1 out of 3, or 2 out of 3. So that means the data at lower dose do not really provide much information regarding the toxicity of dose level 3, the current dose. And then you may say, the other case is we first escalate to higher dose and then de-escalate back to dose level 3. And in this case, how about the data of dose level 4 and 5? Do those data can help estimate toxicity of dose level 3? And for the same reason, it doesn't, right? Because remember, the reason you de-escalate back to dose level 3 is that dose level 4 and 5 must be pretty toxic. You can imagine, for example, those 4 and 5, those 4 have toxicity 2 out of 3. That's why you de-escalate back to dose level 3. And in this case, that's the data in the dose level 4 tell you about toxicity dose level 3 regarding if that's the MTD, not too much, right? Because the dose level 3 can be continued 2 out of 3, or 1 out of 3, or even 0 out of 3. So that means you really can get much information from other doses. And why this is kind of anti-intuitive? This is because dose finding is a very special application. It's a sequential process. That's the first point. And the second point, it's a sequential process from low dose to high dose. You have to go through this process. Only you clear the low dose, you can go up. Only you encounter very toxic dose, you will de-escalate. Otherwise, things won't happen. So because that all the information, most information has been incorporated through this up and down process. And if you borrow through model, it won't help you too much. And if model misspecified, you're going to have a lot of issue. So that's why this happened. Okay. And the second question is, a lot of time people get confused because the BoIN used the p-hat, right? Compare with those two boundary. And the p-hat is point estimate, right? You use 3 patient or 6 patient, 9 patient, you just calculate point estimate. So this makes some people think that the BoIN accounting for the variance of the observed DLT rate in its decision making, right? You have 3 patients you compare with the same boundary, and you have 6 patients you compare the same set of boundary. Should we change that boundary? But as we showed in previous slides, when we derive that optimum decision, the lambda 1J, lambda 2J, it's a function of Nj, right? So that means the whole theory, whole process accounting for the sample size. But magically, the optimal decision is independent of Nj. Okay, so in the bottom, I showed an example to help you understand this sense. Because in this point, in this case, what we're trying to do is make a decision, make a discrete decision, escalate, de-escalate, or stay. And you can imagine we do an experiment, we draw a ball one at a time of its replacement from a bag can contain unequal number of black and white balls. And our goal is to trying to make a decision whether there are more white balls or black balls. And clearly, the optimal decision is always go with the color appeal more frequently, right? No matter you do this experiment 3 times or 30 times. But what's the difference? You do 3 times and 30 times. The only difference is, although the optimal decision is always the same, as long as you see more white ball, you will guess best bet is there are more white ball in the bag. But what's the difference? Difference is when you do 30 times, your best guess, your best decision have high reliability. It's more likely to be correct. But when you have 3, it's less likely to be correct. But the decision is always optimal given the data you have. So this explains why, this in the BoIN and the optimal solution eventually actually independent of sample size. And the next question is FDA granted BoIN a fit for purpose designation and requested some correction. Does the correction affect the use of BoIN? And the answer is no. And if you have a chance to read the correction, you will notice it's mainly to provide more complete and accurate theoretical results on the BoIN decision boundary. and it has no impact on the use of boundaries, the BoIN design. So here, yeah, I should thank, FDA reviewer has done a really, careful and a great job to really verify the theory, go through all the proof, and point out a few, point we overlooked in the original theoretical derivation. Okay, the last question is, given the newly launched Project Optimus for dose optimization, right now people really are interested in this topic, right? Is the MTD funding design like BoIN still relevant? The answer is yes. Why? So remember, what Project Optimus concerns is not the MTD. What it concerns is the conventional approach of directly take MTD as the default dose for later phases trial. So for example, we still need to fund, we can still fund the MTD. And then after that, we identify the safety dose range, and then we can do dose optimization, right? A simple approach is you can randomize the patient into a couple doses, MTD and one dose lower, and then you do optimization. So that means that MTD funding actually is not conflict with the Project Optimus. Okay, so next I'm gonna use a try example
maybe Professor Yuan, before you go to the next part, we do have one question. So do you think we can answer that question before you go to the next part?
Okay, sure.
The question was like, would any statistical consideration available to suggest the starting dose level amount? For example, we say K candidates levels. Is there any?
Okay.
Yeah.
Yes, thank you for the question. So regarding the starting dose, it's more related with preliminary data you have, and also how comfortable regular agency with your choice. And I think from a statistical point of view, of course, in principle, we can start from the dose we think that's most likely to be the MTD, right? Or one dose lower than the dose most likely to be the MTD. But it's first in human trial. We have a huge uncertainty, right? We think, those 100 milligram maybe the MTD. We start from 50. That's safe enough. But a lot of time, the data we have, it's really, really sparse, and sometimes it's just animal study. So in that cases, we typically have to be a little bit more conservative, and I think it's a judgment based on preclinical data and understanding of the drug. For example, you have the same class of drug, or the drug has been used in other indication, and also it's you need a consultation of a regular agency, see if that dose it's a reasonable choice. But we should avoid, choose too high dose or too conservative dose. That will takes a long time to finish the trial.
Okay, thank you.
And I see a second question is, suppose the true MTD is midway between dose level 3 and 4, can BoIN correct estimate the MTD? Okay, so this is a great question. It's also a question people ask a lot. And BoIN make a decision based on the dose, based on the data at the current dose. It does not designate any specific dosage for each dose. It's just say, oh, this is dose level 1, dose level 2. So if you have this issue, what you can do is during the trial, you can add a new dose. So for example, at the dose level 2, you find it's pretty safe. There's even very few low-grade toxicity. And then when you move to dose level 3, you see a lot of very severe toxicity. And in this case, you may add a dose between, for example, middle way between those two doses. And the BoIN design is still applicable because BoIN does not directly associate with that dosage, right? If you look at the CRM, especially the BORM, it's associated with the specific dosage you use. But for the BoIN, it doesn't matter. It's only associated with dose level. It's just a new dose level, no difference. And the other point I want to make is you can combine the BoIN with the model estimation. So for example, if you, in that scenario, you notice dose level 2 is very safe, dose level 3, it's very toxic. And if you want, you can fit a logistical model to fit the curve, help you determine which dose you should put in that middle, right? It can be exactly in the middle. It can be a little bit lower. And you can see those two are complementary to each other. And yeah, the BoIN does not preclude you use the model for help you make some decisions, but it's simple to implement, right?
Thank you so much.
All right, so so that's the two questions I see. And if you have any other questions at the end, you still have a chance. So I'm gonna continue slides, and later on I'm gonna pick up your question if you have. Okay, let me close Q&A this window. Okay, so next I'm gonna show you a case study to show what happened when you use a BoIN design, how it compare with the 3+3 design. Okay, so this is a trial regarding pralsetinib, and we know, I think it followed, so it received FDA's accelerated approval for lung cancer back in September 2020. And later on in December, it's also approved for thyroid cancer. And this is the design used for this trial, and it's called ERA trial. Okay, so this is a kind of phase 1/2 design. And in the phase 1, BoIN design used for dose escalation and identify MTD and the recommended phase 2 dose, and followed by phase 2, which is a multi-cohort expansion, or we can call it a basket trial in different indication. And in this trial, so this shows how the dose escalation occurred in this trial. And you can see this trial started quite a bit number of doses from 30 milligram all the way up to 600 milligram. And this shows the path, how dose escalation happens, and the observed data at each dose. And you can see start from 30 milligram. At the beginning, it's do accelerated titration at the lowest dose, treat one patient, no DLT, and move to 6 milligram, and all the way to 300 milligram. And once reach 300 milligram, there are 2 DLT out of 5 patients. So the per the BoIN design, it's de-escalated. So I think in this design, they used 30% as 25 as target, or 30 as target. I don't remember exactly. It's about that. Okay. So in this case, and every time just compare with those 2 boundaries, and to make a decision, escalation, de-escalation. And the 30 milligram, it de-escalated back to 200 milligram. And 200 milligram, there is a 0 DLT out of 7 patients. So it escalated back to 300 milligram. And one very interesting thing here is when you treat more patients at 300 milligram, for additional 6 patients, there is no any DLT. So this is a very interesting point we should notice in trial. And in phase 1, the sample size is too small. The uncertainty can be huge, right? And the patient also highly heterogeneous. So you notice here, in here, 2 out of 5, that sounds scary, right? A lot talks 2 DLT. But if you treat more, actually this dose is actually pretty safe. So when you put all together, you treat 11 patients, only 2 DLT. And toxicity rate actually even lower than 20%. So this shows a very important, the importance of keep learning dose escalation, de-escalation, okay? And once go through this and they go up again, and eventually at escalate to 600 milligram, they see a 2 DLT, and the trial ends at this point. And the 400 milligram is selected as the MTD and used in phase 2. And in phase 2, it shows very impressive efficacy. That's why it's received FDA accelerated approval. That means in this trial, it's very successful, identify a good dose for the phase 2 part. Okay, so let's imagine if we use 3+3 design, okay, rather than BoIN, what's going to happen? So what's going to happen is if you go through the process, it's going to stop, as I showed here, when we have 2 DLT at the 300 milligram. And then the 3+3 going to pick the 200 milligram as the MTD. And this MTD, or recommended phase 2 dose, it's only 50% of the effective dose actually used in the phase 2 trial. So that means if at the beginning you choose the 3+3 design, you may have a failed trial. Okay, so I hope this example it's help for you if you you're not interested in a new design and trying to convince your clinical team of stakeholder, give up 3+3 design. And in MD Anderson before, clinician always ask me that, okay, do you have evidence? Because they don't understand the simulation, right? Because it's simulation, they say it's not what happened. So so the example I showed, I found it's very effective to educate them, why 3+3 design is a better choice, and it may lead to the failure of your program. And the most scary is you cannot recognize it afterwards, right? Because trial stopped, it's not effective. You think, oh, it's a drug, it's not effective. But the truth is, drug may be effective because you found the wrong dose.
Yeah. Yeah, Professor Yue, we do have a few questions, so hopefully you can answer the question.
Okay.
So the first one is, how small can each cohort be? And the related question could be something like, what decides the cohort size? And how the cohort size selected in BoIN? I think all those three questions are related to each other.
Yes. So this is a great question. For cohort size, when we choose cohort size, we have to balance safety, timeline, and how easy to implement. So when we choose very small cohort size, for example, cohort size 1, we have two consequences. Okay, the one is it tended to be risky. So as we showed in the previous example, when you only have one patient, you can imagine how random it can be, right? Especially phase 1 trial, a lot of time it's all comer. If you get a poor prognosis, that patient has DLT, you will think that's toxic. And also, if you have a healthy patient, you will think it's safe, you're going to move up. So that's why that's the first consequence of use very small cohorts size like 1. And then the other logistic issue is, in all the phase 1, most sequential design, what we need is we have treated one patient, finish DLT assessment, and then we can start treat the second cohort, right? Let's say the cohort size is 1, okay? And we have to treat the second, and then we can treat the second cohort. And then we have to finish DLT assessment. Typically, it's 21 or 28 days, right? For some immunotherapy, you may use 2 cycles, 3 cycles. That's even longer. And when you use very small cohort size, given the same sample size, that means you have to wait many times, finish DLT assessment, and then treat the next patient. So that may make a trial very long. Okay, so that's the downside when you choose the very small cohort size. But the advantage is you have more chance to update your estimate to make adaptive decision. So that means you have more freedom to move up and down, which may improve the accuracy of identified MTD or the trial efficiency. Okay, that's the strength of using smaller one. Okay, on the other hand, if you choose the large cohort size, the downside is, imagine if you have 30 patients. If you use cohort size 6, that means you only have 5 cohorts. If you have 5 dose levels, that means at any time, if you stop, you cannot even reach the highest dose. So statistically, that means you have less degree of freedom to move up and down to adaptive learning. You are very easy to stuck somewhere, and you may totally miss your target. Okay, that's the first downside. And the second downside is it's also have some safety concern, especially if your accrual is very fast. Okay, so let's say you have quickly put 6 patients on 1 dose, and then you realize it's very toxic, and there is no chance you can make a decision within that 6 dose, right? Let's imagine you have 4 DLT or 3 DLT. That's too late. So that's also another downside. Of course, when you use large cohort, the advantage is you have make less adaptive decision, which logistically can be simpler, right? And the other thing is sometimes it can save your trial duration because you only have to wait only after DLT assessment for the whole cohort. That means within that cohort, you don't have to wait. You just continue treating patient. And then after treated last, you wait DLT assessment window for the next cohort. So that's the strength of use large one. Actually, if you want to balance those two, actually 2 or 3, actually it's a good choice. Okay, I go in very long way, but that's I just trying to help you understand all those consideration under the cohort size consideration. So typically, 2 or 3 it's a good choice. But for the BoIN design itself, it doesn't matter. You use 2 or 3 or 4 or 5. It doesn't matter because it's always based on the observed DLT rate. And that's I think since we already have some time, and I also answer some question. And the other common question I receive from many people is, if I plan cohort size 3, and I happen 1 patient dropped out, or I over-enrolled 1 patient, I get 4 patients. Can I use BoIN? Is it okay? And in general, it's okay. And I think that's also one strength of BoIN compared with 3+3. And when you 4 patient, 5 patient, sometimes you cannot make a decision because the design does not tell you what to do when you have 4 and 5 patients. Sometimes you have 7 patients, right? But in this case, the BoIN doesn't matter as long as you can have data. You can always estimate the DLT rate. You can always make a decision based on the compared to those 2 boundaries. And we have a paper specifically investigate this issue. As long as you are not always intentionally changing the cohort size. So for example, I don't see DLT, I change it small. I see DLT, I make it big. As long as your cohort size deviation, it's not depends on the data. Okay, for example, it's more due to randomness. Some patient drop out, some patient are invaluable. That's most times it's okay. And it's OC, it's very similar to the fixed cohort size you originally planned for. Okay, that's regarding the cohort size. And I see another question based on the case lung cancer example. Can we say the standard 3+3 design is more conservative than BoIN? That's yeah, I think in that specific data, that's the case. And in terms of general operating characteristic, right? Because we cannot determine the operating characteristic design based on one realization because data is random. And in general, 3+3 design, one of the drawback or criticism for the 3+3 design, it's very conservative. Okay, so that's the issue of 3+3. And the real issue for the 3+3 design, it's too easy to stop. Whenever you see 2 DLT, you will stop. And you can imagine we only have very few patients, 3 patients, 6 patients. So the randomness is really high. So if you are unlucky have 2 DLT, you don't have any chance to reassess that dose. Even that 2, it's due to randomness. So that's what we see in that trial for 300 milligrams, right? And at that time, it looks toxic, you have 2 DLT. Later on, you put 6 patients more, no DLT at all. So that means the first 2 DLT may be just totally due to randomness, or you unlucky, you get a very poor prognosis patients. So I think, yeah, that's my answer. I think the real problem of 3+3 it's too easy to stop, and there is no chance you continuous learning the dose toxicity profile. Okay, so next one, in that case, study would add 500 milligram after 600 milligram be an option, dose jump. Yeah, I think if as I said, if the data at 50 milligram, it's very safe, 600 milligram, it's very toxic. Yes, you can. And also, so remember in practice, what we will do is it's not only look at the DLT, right? You will look also low-grade toxicity. You will also look at the PK saturation. And if all those data support 50 of 6, if all support 400 milligram, it's too low, and 600 milligram it's too high. Especially you can based on the PK information. If that support, you should add a 1 in the middle. Definitely you can. And also, you can just take a simple approach, do a linear extrapolation between those two doses, or you can take a more sophisticated approach, fit a logistical model, and help you estimate, what's the dose you should put between the 400 and the 600 milligram. Okay, next one. Do you normally feel that the clinical team are willing to use tight design to mitigate the issue with a small cohort size? Okay. So here is my recommendation. If your DOT window, it's not excessively long, it's more kind of in typical case, right? 21 days, 28 days. And in this case, I won't use the tight version with a small cohort size. So the reason is this. So whenever you use whatever tight design, no matter it's tight BoIN, tight CRM, so basically behind the scene, what doing is you based on the observed data, make prediction what's going to happen for those pending patients, so you can make early decision. And clearly you can see when you do this prediction, you add another layer of uncertainty on the small sample size. So which could be, cause a more noise. So in that case, I don't think, use the, a larger cohort size like 3, it's a better option. But of course, in the case, if your DOT assessment window is very long, like 2 cycles, 3 cycles, and in this case, I think a tight design is a good option because there's no way you're out of it. And if you want to save time, you have to make prediction, right? And in that case, you can use cohort size 3 and help you get some data. And so you can make a relatively reliable prediction to make decision, early decision for dose escalation, de-escalation. Okay, so that question. And then next question is, how would the BoIN suite be best used to get the most accurate simulation results in a scenario where you require an initial minimum cohort size 3 for each dose level, then allow the cohort size to increase by 1 after the initial cohort size 3 for a dose? And is this a reasonable cohort approach? So first, I think this is a reasonable approach if you have constraint on the sample size, right? For example, it's very expensive and you have very short timeline and you want to finish phase 1 trial. It's a reasonable approach. And the catch is, as I said, when you treat by cohort size 1 and given the same period of time, because the DOT window you have to get cleared before you treat the next patient, and you may it may lead to a long trial. And of course, you will say, okay, can I use smaller sample sizes so the total trial duration is still okay? Yes, you can do that. But when you do that at the end of the day, maybe you only end up with very few patients at your MTD or the dose around the MTD. And I think most of our audience, familiar with the Project Optimus, right? So I think the whole purpose is one, you treat a little bit more patient, so you can get more understanding about the benefit and the risk of dose, and eventually help you identify the optimal dose. So if you take this approach, you will end up with very few patients, and it's a little bit conflict with that concept. But I think if you do it in the right way, and it depends on the disease setting, depends on your prior information, it's possible, right? So for example, you use 1, and once you identify the MTD, and then you can do cohort expansion or multiple dose expansion to address those optimization issue. Okay. I see another question. In the example, it was de-escalated from 300 milligram to 200 milligram to 300 milligram. When calculate DLT rate at a second 300 milligram, it's the number of DLT at the first 300 milligram not included. Okay, so this is a very good question. And this is also the key when you use the BoIN design. You always use all the cumulative data at the current dose, okay? Not the data from most recent cohort. And then you can imagine it doesn't make sense, right? At the same 300 milligram dose, you previously treated 5 patients, you ignore that data. It doesn't make sense. And the BoIN doing is you just use all the data based on all you observed to make a decision. And in this case, in this specific case, it will be based on 11 patients. You have 2 DLT.
Thank you so much. I think that's all the questions so far. I think you can continue your presentation. So if we have more questions, we can answer them in the end.
Let me close this Q&A window. Okay. So next is going to be pretty quick. It's just to show the software and BoIN suite to help you use those designs. And I think many of you may already tried it before. It's trydesign.org. And if you go there, so there's an array of different designs for different settings, phase 1, phase 2, phase 1, 2 basket, and platform try, and so on. And the BoIN suite is over there, and it's also it's called, the reason it's called a suite, it's because it's including various BoIN design to address different clinical setting, and there is a decision tree to help you choose which design you should use. And at the top of the tree, at the first question is the goal is to find the MTD or OBD. Right. So let's say if we trying to find the MTD, we go to the right, and go to the right, and the next question is you do a single agent trial or combination. So remember, in here, combination means you do a trial, you're going to vary the dose of 2 drugs at the same time. So basically, you find the MTD within a matrix. Okay. If you do a combination trial, 1 drug is standard care, it's already fixed dose. You add another new drug, vary the dose level. It's from design perspective, just single agent. Okay, don't get confused in that one. So here, single agent or combination, more from a design perspective. It's not, just do you combine 2 drugs? Okay, and if you do a combination, trying to find the MTD from a combination matrix. And in this case, you can use a BoIN combo design. And if you are single agent, and then do you want to incorporate prior information or not? And if you have reliable prior information, and you can use iBoIN, means the informative BoIN. And if it's no, and the next question is toxicity late onset or not? And if the toxicity late onset, your DLT window is very long, like you do radiotherapy or some immunotherapy. And in this case, if it's very long, becomes infeasible. In this case, what you can do is you can use tight BoIN to accelerate your trial, and if it's not, you can use standard BoIN. So this is for the MTD, and on the left side is the OBD, and which can be pretty useful for Project Optimus. And in this case, you also can have a different choice. And in here, so we put the question as MTD as second objective. And it's not a very, I think that clear question, right? The reason we do this is you notice here, there's U-BoIN and the BoIN 1, 2. The real difference between U-BoIN and BoIN is U-BoIN is a 2-stage approach. The first stage is identify the MTD and followed by randomization among several doses. Okay, so that's why you can see from the structure in that approach, you first trying to understand the MTD, and then you're trying to optimize. So that's where you put the question, MTD is a secondary objective or not. If it is, and then you can do U-BoIN. And the BoIN 1, 2, it's a more efficient approach in the sense, from very beginning, it's always a target, the optimal dose. that maximize the benefit risk trade-off. So in some sense, it will be more efficient because it's not first find the MTD and then find the optimal dose. It's directly trying to find the optimal dose. And in this setting, there is, again, you have a late onset or not. Because in this approach, one common question and a practical issue is toxicity may be okay, but efficacy often take a little bit long time to be observed, maybe 2 cycles, 3 cycles. And in this case, it's difficult to make a decision if you want your decision always based on the toxicity and the efficacy. So that's why in this case, you can choose a tight version, tight BoIN 1.2, and to help you make early decision. You don't have to wait too much. Okay, and this is the the interface of the BoIN suite, and you can see those different choices actually in different panel, and you can choose what suitable for your trial. And so the last one is the reference, and this is the book I think published a few months ago, and many questions you guys asked. I already, answered and described in this book. And for example, how to choose cohort size and if we have a cohort size deviate, what's going to happen? And also including all the, FAQ I put at the beginning, right? Some people theoretically have some question or, about it, So if we ignore other doses data, it's more efficient or not. And, if does the decision depends on the size, sample size or not? Those I already explained or in this book. And I think one other feature of this book is for every design, we have a section about a real case study. And it is a step-by-step guidance on how to use a BoIN suite, the software we have at trydesign.org, and step-by-step demonstration, how you use it and what's the meaning, and at the point that you should pay attention when you use the software or fill in each parameters. And so we are very happy finding, it's #1 new release in biostatistics. So if you are, if you are interested, I recommend you read this book, and it covers all I talk about today, actually more. So most importantly, buy the book, I get rich, and then retire.
Yeah, thank you so much.
Okay, thank you.
Yeah, thank you so much for the great presentation. Also, thanks a lot for answering so many questions from the attendees. I think we only have one last question in the chat box. So the question was, how BoIN can play a role in dose optimization to address FDA's Project Optimus? So, okay,
I think I briefly mentioned this when I talked about the decision tree. I can talk this a little bit more. I think it depends on the setting. You can decide what approach you can take. One simple approach, at least straightforward one, is you can still use BoIN to identify established MTD. And then you do cohort expansion at the MTD and a lower dose. So for example, you randomize, 15, 20 patients to the 2 doses. And eventually, based on the totality benefit and the risk data, pick one that have a better benefit risk profile as your recommended phase 2 dose. And so that's one approach. And for this approach, the advantage is it's pretty straightforward, right? And still align with the traditional thinking and the paradigm. And also it takes stepwise approach. First I find MTD, establish the safety set, and then I consider about look at the causes, and eventually pick the best one. That's one approach. And the second approach is this approach. In general, it will need a little bit big sample size, because you first have to reliably identify the MTD. And I think another question people typically ask me is, when I use BoIN to find the MTD or do phase 1, what's the sample size I should use? And a rule of thumb is number of dose times 6. Okay, that's also described in my book, and that's a ballpark estimate. And again, based on your real trial setting and the constraint, and you can calibrate that a little bit. So, for example, if it's very safe, you can do a little bit of accelerated titration. That means you reverse one of the question approach our audience suggests, right? In that approach, it suggests, you do 3 and then change cohort size to 1. In that approach, you do cohort size 1 and then switch cohort size 3. And I think in the BoIN, it have no constraint or requirement. You have to fix cohort size. In principle, at least you can always you can modify the cohort size. And the other approach is, as I mentioned, is you can use BoIN 1.2 or tight BoIN 1.2, which it's more efficient to identify the dose, optimal dose. And because at the very beginning, it's target the optimal dose, and based on the risk-benefit trade-off. And I get involved, the trial use both of design. And so far we get, we have favorable experience with FDA when we submit those trials to FDA, and both approach seems, we don't have any trouble to use that. Do you think if approach have similar benefit for small molecule biology, cell and gene therapy? Yes, the answer is yes. For those, as for example, for CAR-T trial, and a lot of CAR-T trial use the BoIN design or BoIN 1.2 design, and at a higher level, we're just trying to assess the risk or risk benefit at the same time. It does not really relate too much with the property of the therapy, right? Of course, different therapy have a different consideration. So, for example, how long is the DLT window? How long is the efficacy window? Those will be different across different therapeutic area. But at a little bit higher level, those are the same. Our goal is, once you define those endpoint, and endpoint may be different. Once we define the endpoint, eventually it just becomes what's the risk, what's the benefit, right? You want identify those fits your objective.
Okay, sounds great. I think we already 10 minutes past. I think your presentation generates a lot of interest from the attendees. I think probably we should stop here. And if the attendees have any follow-up question, you can always reach out to Professor Yin Yuan. So that's it. And Wenting, just maybe you want to say something before we close the session today?
Yes, thank you, Zhaoyang. And this is great. And first of all, I want to sincerely thank Professor Yuan for giving such impressive talk today. This is very influential work. And as Dr. Yuan said, this is the first dose finding method that has granted the fit for purpose designation from the FDA. And today's talk is very impressive and very clear, and looks like Professor Yuan and his colleagues are the master chef that prepared many delicious dishes. So there's always one that will fit for your purpose and fit for your needs according to the decision tree. And I also want to congratulate Dr. Yuan for the new released book. I think it will be a very valuable textbook to read.
All right, thank you.
Yeah, thank you, Dr. Yuan. And I also want to thank Dr. Zhaoyang Ten for moderating today's webinar and for the help of the logistics. And lastly, I also want to thank all of you who attend this webinar today, and all the very interesting questions you have raised. And if you like this webinar, you may be interested in other webinar and events that are hosted by the Boston chapter of the ASA. We have many exciting events planned for the year 2023, including the Most-Stellar Statistician of the Year Award reception, and of course, the 2023 Boston Pharmaceutical Symposium. You can learn more about those upcoming events on our Boston chapter website, and you can also find us on social media by searching for Boston chapter of the ASA or BCASA on LinkedIn and on Twitter. We are very looking forward to seeing you at our next event, and thank you for attending today's seminar, and bye for now. Thank you.
Thank you.
Everyone.
Thank you.
Bye-bye.
Bye-bye.
Bye.